data together, and then you party on the data, right? So that's not Voelfel-Wabbit. Voelfel-Wabbit is an online learning system. That's very different in many ways from what you're used to. It also has a lot of other tricks that you'll see, which are very, which push the extremes of what's possible, because it was kind of driven by the kind of research that I was doing at the time that I was working on it. One of these is large-scale linear regression. This was the first terascale learning system. It's designed to operate in a Hadoop environment on 1,000 nodes. Another one is active learning. I was talking to Claudio just a moment ago about active learning. There's a number of active learning algorithms. So in active learning, what happens is your learning algorithm is kind of guiding which points you want to have labeled. So it goes out and says, oh, I would really like to have this point labeled. Can you label that for me? And the goal there is to try to figure out how to get good performance with as few labels as possible. Another kind is learning reductions. So back in the day when I first started doing research in machine learning, everybody was creating a different learning algorithm for every different problem. And that kind of seems chaotic. So I spent a lot of time trying to figure out how to turn one problem into another problem so that the solution on the problem you reduced to would give you a good solution to the problem that you started from. So VW operates through reductions to a large extent. There's everything kind of reduces down to a base learning algorithm. There's also learning to search. So maybe I should update the name here. Nowadays they call this reinforcement learning. Back in the day, it wasn't called that. It was called learning to search. The idea there is that you have a simulator, and inside of this simulator you're making discrete decisions. And at the end of a sequence of decisions, you get some sort of feedback about how good the outcome was. And now your goal is to improve on some policy that you start with, right? Based upon this reinforcement feedback. So we've done a lot of tricks with this to make it so that you can do complex structured prediction problems like dependency parsers using this kind of approach. It gives you good performance. But I think the real value of this is actually in relatively ad hoc pipelines. If you have a long pipeline of decisions that you want to make, which has some feedback at the end, you can start optimizing for that long pipeline, even if parts of that pipeline are code or some other process, and then parts of it are learned. So you can have a mixture of code and learning in a manner which is relatively unique. Another area I've been thinking about a lot is how do you choose one of k things in time logarithmic in k? This is a research area, of course, but if you wanted to build a face recognizer for everybody on Earth, you'd really want it to run in logarithmic time because there's a lot of people on Earth, all right? You probably want to apply it many times. So there's several different algorithms inside of VW now for doing this, and they actually do interesting things at times. And then the last topic here is contextual bandits. So what I was planning to go through for today is primarily the first thing and the last thing. So contextual bandits are sort of one-step reinforcement learning. So what happens if you care about your immediate reward for whichever decision you make? Because that is the kind of reinforcement learning which actually gets used in the real world and which does great things when you can use it. So are there questions about this? As I said, you should feel free to ask questions because I'm entirely happy to go in any other direction that interests everyone. Okay, so just a few high-level things. As a BSD license, it has a fair number of people who are using it. It's been used by a large number of different companies. There's an automated test suite. There's a GitHub repository. You can essentially do all I/O modes. So there's an executable. That's what I primarily use, but there's a library also, and you can connect to ports, and you can talk to it as a daemon. There's also an input format. Now, the input format can kind of handle sparse data of the sort that you might be used to, but also a much more rich input format where you actually just feed in raw text, and it will do something interesting. I'll show you a bit more about that later. It's mostly C++, but there are bindings in other languages. Python, C#, and Java bindings are all pretty good. Right, so yeah, so this is an open source project. Obviously, many people have contributed to it over time, and so I thank all of them because it's made things much better than I could ever do myself. Okay, so let's start with online linear learning. So this is kind of what the baseline default is in Voppelwabbit. So what happens is, let's see if I can do this. Yes. So you get some features, and then you make a prediction, and then you observe some label. Interesting. Here, does this work? Okay, good. So you get some features, you make a linear prediction, and then you observe a label, and now you update your weights, right? And there's a number of different ways to update the weights, and there's many variations, but this is the core idea. There's also, you can do logistic instead. These are kind of minor variations, and all the minor variations you might expect are supported. Okay, so as an example, if you're optimizing squared loss, what you might do is compute the gradient of squared loss and then update in the negative gradient direction, which is exactly what this update would do, right? Where eta here is just some learning rate. Now, if you do that, just that, it ends up not working terribly well. But it turns out if you optimize the way you do the learning, exactly, so with variations on this, you can make it work pretty well. Okay, so let me show you an example. This is let's go here. Right, so this is the kind of data that you might be used to. So there's labels, 1, 2, label 1 or 2. There's features, so feature 13 has value 3.9 times 10 to the minus 2. There's a whole bunch of features for each individual thing. This is a document classification data set, RCV1. Okay, so if we look at this in more detail, let's make that a little bit more readable. 1.1 gigabytes. We can ask how many lines are there. Takes a little while. It's about 760,000 lines. Okay, I'm bored. All right, so then we can try to learn. So we just want to run through the data set, learning. We're running online. So we're going through each individual example. I guess it was faster than WC. Huh? All right, so we went through each individual example. Oh, wait, microphone. We went through each individual example. Okay, and now I need to tell you a trick. So the trick is, okay, so if what you did was you did train and then test in the normal batch way, it'd be very slow. You wouldn't want to do that. Right? So instead what you do is you test one ahead of where you train. Right? And that also gives you an unbiased estimate of performance. And so this is the performance since the beginning. This is the performance since the last line. We're printing out with some sort of exponential back off. One of these is the prediction and one of these is the truth. This is the example number that we're on. This is the number of features that were associated with that individual example. We finished the run. We went through 781,000 examples at 781,000 lines. Our average loss was 0.05. Now remember, this includes the average from the beginning when we didn't know anything. All of our parameters were initialized to 0. Yeah, so we'll keep going. There are about 60 million features here. So overall, yeah, we got a decent result. And we did it in about 3 seconds, which is not bad. Okay, so this is something I could have showed you 10 years ago, because we had this working 10 years ago. And there's a lot of tricks and things that have been layered on since then to make it better in many ways. So one of those is we have a more sophisticated update rule, which allows us to get somewhat better performance. Another one is this hashing trick. So let me show you this. Yeah. So this is the data set in as a raw form as is available, essentially. You have the same labels, 1 and 2, but now you have some words, they're stemmed because the data set, so I can get it in the rawest form, is stemmed. Some stop words have been removed, but these are the actual words in the documents you're trying to classify as business documents or not, right? Okay, so we can go and let's do just this one. So we're running through, going through things pretty fast. Our performance ended up a little bit worse here, 0.057. I should get my mic. Our performance ended up a little bit worse, but we're working with the raw data. So we've eliminated a lot of steps in our pipeline. And now we can start doing things like saying, oh, I would like to play with n-grams. So I'm going to have bigrams. So I'm going to, let me make this a little bit taller. There. So first of all, how did this work? So you had the individual words. I used a hash function to compute an index into a parameter array for each individual word, and I treated a non-specified value as 1. Right, so that gives you a bag of words representation, and then you can just work with that. I can change the number of bits in the hash function, changing the number of parameters to be 24 rather than 18, which is the default. It gives me a little bit more parameters. I can say, oh, I want to work with bigrams, and I want to allow skips of 4 between the elements of the bigram. And then I can, this is just saying I want to print out the binary loss. I can also say I'm going to adjust the learning rate down a little bit. The default learning rate is 0.5. 0.25 ends up working a little tiny bit better. Okay, so now if I do this, it's running through things. It's a little bit slower now because it has quite a bit more features that it's generating on the fly. But it's still pretty fast. It's at 262, and more importantly, the error rate is getting lower and lower and lower. Right, so almost there. Right, so let me push this up a little bit. 0.045, which is really good performance on this data set. So just by switching to working with the raw data and playing around with exactly which features we wanted, suddenly our performance became much better than what you could get with any sort of TF-IDF linear on the original words type of thing. Right. So this is kind of the core of EW. Are there questions about this? Yeah. What's that? No, this is just 0-1 loss. So I can, if I get rid of this, then it just does squared loss, which is the default. But then you can also do logistic or whatever you want. Yeah?
Can you explain how the hash works and how the feature space translates to the hash space?
Yeah. So for every word, you compute a hash. You use a 24-bit hash here. And that 24-bit hash is a number, which looks up a point in an array. And the parameter at that point in the array is what gets used when you're learning for that individual word. Now there's a complexity here, which is that we're also doing, let's go here. We're also doing bigrams with skips. And what's happening there is you have the hash of one word, and you have the hash of another word, and you combine them, right, to get a new hash. Right, so it's very straightforward, amazingly useful trick in my experience, because it lets you work with raw data in a way which is just much more natural than other approaches.
So would you get the similar improvement? Instead of working with raw data, you work with pre-processed data, AF/IDF, by using pairs of features instead?
Yeah. So yes. So we're not manufacturing information. You could work with bigrams, and then do a TF-IDF transformation on it, and then try to get good performance. And you probably will get good performance. It would be similar to what you get here, right? This gets you most of the performance that you could possibly get on these kinds of linear, sparse text type things, which is where VW is really good, with very minimal effort. Another question?
One more.
Is there a simple way of adding a word?
Is there a simple way of adding a word embedding? So there is a way of adding a word embedding. I wouldn't call it simple. But basically, you can. There's an option. You can feed it a dictionary, and it will substitute things in from the dictionary at runtime. Okay. All right, so we can get pretty good performance. Okay, so now, another question?
One last question.
Yeah.
Isn't the number of bigrams surprisingly low? You have 300 million bigrams and 16 million features.
So remember, we're considering skips. So we're doing bigrams for adjacent words, then also 2 words with a star in between, and 2 words with 2 stars in between.
It's only 6 times more.
Yeah, that's actually correct though, because we're only counting the number of that actually appear. Right. So let's go back. There. 344 million. But if you think about it, if I give you, let's imagine that we're not doing skips. Let's make it simpler. So you have a sequence of 100 words. How many bigrams are there in that sequence of 100 words? 99. So if you allow skips, then it gets a little bit larger, but it doesn't grow fast, right? The set of potential bigrams is extremely large, but the set of bigrams you actually encounter is not so large. And so one of the things that happens when you're doing this hashing thing is you end up learning a relatively robust predictor. And so back in the day when I was at Yahoo, we would use things like this. You wanted a robust predictor because it meant that an adversary couldn't come in and, pick a word over and over again that would break your system that easily. Okay, so why do we want online learning? Why is this interesting? So you get very fast convergence to a pretty good predictor. So I think that often if you want the very last bit of performance, then you don't want to be doing online learning. But it gets you into the neighborhood of the best possible very quickly. It's also very RAM efficient, right? So I guess these days, the amount of RAM on a laptop is relatively large, so I can easily fit the data set into RAM. But on the other hand, I can also shove data sets which are much larger than RAM through the learning system. without it even being bothered. So there's a duality between online learning algorithms and online optimization algorithms. So many of you are operating in a batch learning paradigm. And what that means is that you really are doing online optimization if you're doing kind of an online gradient descent type thing, because you run over the data set over and over and over again in order to get the best performance that you can. So I guess from a research perspective, studying online learning is very interesting because it also means you're studying online optimization, which means that there's kind of two applications that you can think about. But at the same time, when you're helping batch people, when you're helping people solve batch problems through online optimization, you're also attacking how to solve truly online learning problems. Things where the data just comes at you and the problem is shifting and you need to be able to keep up that shift in the problem in order to get the best performance that's possible. Yeah?
Very quick question, just from what you're describing, is there a meaningful difference between what you just showed and something like stochastic gradient descent? Like a conceptual or meaningful difference?
What I showed you is stochastic gradient descent. It's one pass stochastic gradient descent. And it's using progressive validation so that you can actually discover what your performance is as you're running through the data set. There's been a number of times when I was doing some machine learning task and I discovered that things were wrong before I even finished one pass of the data. And then, you can debug very fast. Other questions? Yeah?
You have to worry more about overfitting in this scenario?
You have to worry less about overfitting in many ways. Because, okay, so if you're passing over data many times, then overfitting becomes a much more serious issue. But progressive validation, where you're testing one ahead of where you're training, has the same kinds of unbiased estimate properties as a test set. So that's really nice, right? It means that that you can have an unbiased estimate of the performance that you're getting, assuming the world is coming from an IID source. Yeah?
Sorry, speaking of debugging, what kind of debugging tools are available? If you stop it in the middle or something, to help widen the signal?
Yeah, so there's a lot of tricks actually for debugging. I don't know how many of them I should try to tell, but all right, so presently the strings just get destroyed by the hash function, they go away, right? You can of course say --audit and then it will print out exactly which examples are going into the core learning algorithm with the features in full text form. You can do the same thing, except you can do it in the model. So you can figure out which parameters associated with which features in the model. Now these are slower, right? So you pay a penalty, but you can do that, right? And then there's more advanced forms of debugging available as well. So, for example, you can say, I want to do some L1 regularization. And the BW L1 regularization is applied on a per example basis. So you use so it's 10 to the minus 6. So it's a small, gentle amount of L1 regularization on a per example basis. So then you run through, your performance is not really harmed, it's a small amount, but the parameters which don't really matter, they'll get zeroed out, right? So this is more like data scientist debugging. We're trying to figure out which parameters really matter, and you can do that in bulk for all of the parameters simultaneously using L1 regularization, right? And there's another trick, which is, this is a true online learning system. And that means that the state of the learning algorithm can be captured. You can save it to a file, and then you can start it up again and continue on a stream. And that means that if you have something weird going on halfway through your data set, you can just cut your data set into two. You can train on that first half, save it with save resume, and then load up that model and finish and get the exact same result. So you're guaranteed to be able to, that you're not losing any information. Right? So those are the kinds of tricks which are available. Right. So the last thing here is that online learning is actually a thing. There's a number of problems where the problem changes over time. And because the problem is changing over time, you really need to have a learning system that can keep up with it. Okay, so this is half. It's also the reinforcement learning side. And the key thing here is that you really can't do online learning without thinking about reinforcement learning. And the key reason here is that the kind of information that you get is just different. So many of you are used to supervised learning. In supervised learning, what happens is you have unlabeled examples and you hire some people to label things, and then you shove it into the machine and out comes a classifier, right? This is kind of the supervised learning paradigm. and it's cool. People have done lots of things. This is ImageNet. But, okay, so when is a supervised learning problem? When supervised learning, right, you think of it as solved if a human can tell you the right answer many, many times. Right? So you have 1,000 penguins in ImageNet. Okay, so supervised learning doesn't always meet that contract, but this is what they're aiming for, and this is I think what a lot of and now I want to tell you that this is so supervised learning is a tool to teach machine known things, and now it doesn't work when you really want to do things that people don't know. So suppose that you want to recommend news stories, right? You observe people not clicks. And it turns out to be quite hard. So in a standard pipeline, what happens is you construct features of the user in the article, and then you try to build a predictor of the probability of a click given the features of the user in the article, and then you choose the article which maximizes the predicted probability of a click, and then you deploy this in an A/B test for a couple weeks, right? And I've seen this fail a number of times. And now the question is, why does it fail? People peek. So there's sort of two things that I think go wrong systematically. All right, so is Ukraine interesting to John? Claudia knows the answer to this. Yeah? What's the answer? Yes. My wife is from Ukraine. But you wouldn't know that unless you actually displayed a news story about Ukraine. Or an editor wouldn't know that unless they actually knew my background in great depth and detail. Right? So this is one of the real fundamental limitations of trying to do supervised learning. You need the right signal to get the right answer. And supervised learning is not about getting the right signal, it's about using the signal that has been given to it. Right? Supervised learning is a process of transferring information from. The other thing is that the problem is truly non-stationary. The set of interesting news articles changes rapidly over time. This is real data, where we took a model from day 1 and we deployed it on day 2 and day 3, and we observed that the performance was substantially worse. So it was actually, this is one of those problems where things shift rapidly. And so you need to use some sort of online learning to keep up with what's going on in order to get the best performance possible. Okay, so now the question is, how do you actually handle this? And the answer is, you think about a different kind of feedback. You think about good and bad. We're thinking about some sort of reinforcement feedback. Now the question is, how do you learn from a reward signal? Okay, so this is reinforcement learning. So you have some observation that comes in. This is a different paradigm from supervised learning. So you have an observation that comes in. You have, and that could be the user history and the news stories. You have a learning algorithm with some policy, which needs to make a choice, a different news articles. And then you choose some news story, and then later on there's a feedback. Maybe there's a click or no feedback or no click, right? Okay, so I've worked on these kinds of things for a long time. And there's a lot of fun examples of this. So backgammon was solved in the 1990s before I was a graduate student. And then more recently, people have been playing with Atari games and Go. And that's actually quite a bit of fun. Okay, but there's a caution here that I want to make sure you're aware of, which is that these were all PhDs doing these problems, and it's super necessary for that to be true. So I'm going to tell you a simple problem that breaks all the common reinforcement learning algorithms. So a boy goes camping. It's his first day camping. He has a fire, and the fire starts to die down. It's getting cold. What he should do is go to the logs and get a log and put it on the fire, right? But okay, so maybe these algorithms kind of do an epsilon greedy exploration. So with probably epsilon, he steps away from the fire, right? And maybe epsilon squared, he steps away even further. But then he starts to get even colder. And so the obvious thing to do is to step back to the fire, right? And so the boy is warm for a while, and then the fire goes out, right? So this is a very simple problem, and this breaks common reinforcement learning algorithms. Go and read about the policy gradient alternatives people use these days. So if you have t steps to get to the solution, the probability of you getting there is like 1 over epsilon to the t. If epsilon is 0.1, then and t is 20, then you're looking at 10 to the 20, and that's not even a significantly large problem, right? So this is a real weakness of the multi-step reinforcement learning that you see in the kinds of games people are playing with, right? And people figure out ways around this. And if I had, I didn't prepare, but I can go through a bunch of tricks people use to get around this. Okay, so the one trick which I really want to emphasize to you is one-step reinforcement learning. Right? So if it's this case that you're optimizing an immediate reward, then it turns out that everything I just said is wrong. You can actually do this. You can even do it systematically. So that is really cool. That means that suddenly you can widen the scope of problems that you can hope to solve. Okay, so this gets used. It gets. I've had a number of papers on this. News recommendation, when I was back at Yahoo, was the first application we worked on. It's been used for ad choice and ad format and education and music recommendation and even robotics. That's a pretty cool one. So in robotics, you would think that it's a very stateful. Oops, I need the. Right, sorry. In robotics, you'd think it's a very stateful problem. And so you really need to have a multi-step reinforcement learning paradigm to solve it. But in robotics, you also have a physical system which is moving in the real world, which means that the samples are incredibly expensive compared to computing in a GPU or whatever, right? And that means you need to be as efficient as possible. So there's a division of labor that goes on in this particular application. What happens here is the human figures out a short-term proxy reward for what they want to optimize in the long term. And the learning algorithm optimizes that. And that I think is something to think about. Whenever you have some sort of long-term reward that you want to solve, if you, as a human, can figure out, or as a data scientist, can figure out how to break it down, say, this is what I want to optimize in the short term, this is what I want to optimize next in the short term, and then they'll let the learning algorithm solve that, and then you can solve much more complex problems than you might otherwise be able to solve. Oh yes, and the last one is wellness and health. So this is things like encouraging people to walk more, right? It turns out that these kinds of techniques are very useful there. Okay, so there's a tutorial that we taught at 2 ICMLs ago, which is online. You can go and look at it there. All the technical details are there. And the algorithms are in BW. Okay, so we are in fact playing with a service. And if you want to play with a service, like a cloud service, this is where maybe I get smited by Google, but we're having fun. Come and join us. And I wanted to show you what this actually looks like as an algorithm as well. Let's go here. Not there, this one. So how much time should I take? Okay, so I'm going to show you guys more detail first before I show you the algorithms. Right, so oops, let's go here. So I want to tell you just a little bit more about how to think about this. So we're thinking about a contextual bandit problem. It's not supervised learning. It's a one-step reinforcement learning, also known as contextual bandits. So what happens in contextual bandits is you observe features, you choose an action, and then you observe the reward. And now you're trying to maximize your expected reward. Okay, so there's a really cool trick. Okay, so let me tell you a little more. So a policy maps features to actions. So you should think of a policy as just being a classifier. It's just that I have an additional meaning when I say policy. I mean something which actually takes actions in the real world. Like for a classifier, it might be just advice for some other system. But here I mean something which actually takes action in the real world. So it could be a neural network, it could be a decision tree, and a policy is a classifier that acts. Okay, so when you're trying to solve these problems, you're trying to gather the information necessary to solve the problem. And so that in order to discover that John is interested in articles about Ukraine, you have to actually explore across different articles to some extent to discover the information that John is interested in Ukraine. So instead of having a deterministic policy, you actually have a randomized policy. And I don't mean a uniform random policy, although that's possible. What I mean is the best algorithms are all smart randomization. So an example of this would be something like you train 12 models and you randomize which model you ask what to do. Right? So maybe sometimes it's a space article, sometimes it's a food article. Okay, so now here's the really cool trick. The really cool trick is, okay, so we're collecting this randomized information. So we have the features, we have the action, we have the probability of the action that we took. And we know this because we drew from that distribution at the time that we chose the action. And then we have the reward, click or not. Okay, so you have this information, you have a data set of that sort. So this is different from a supervised data set. In a supervised data set, you would just have the label y. And you have some policy. Now, the most basic thing that you would like to do is know how good is this policy. So in supervised learning, this is easy. You just apply the policy and you see what your loss is, right? Just taking an average over your data set. Here, it's a little bit more tricky, right? So the standard answer is you ignore your data and you go and deploy the policy in the real world. That is the standard answer, right? So it's called A/B testing, and it's horribly inefficient. What you might want to do instead is something like this. We want to value a policy. We're going to take an empirical average over the data of the reward times an indicator function, which is 1 when the policy's chosen action is equal to the random action, divided by the probability of the action. So this formula is reasonably intuitive to most people. You expect a large reward is good. You kind of expect to pay attention to the data which agrees with the policy. The division by p is maybe the least intuitive part. But it turns out that this is, in fact, an unbiased estimator. So you can prove that the expected reward of the policy's chosen action is equal to the expectation of this estimator. And that proof fits on this slide. What you can do is you can say, I'm a researcher, you have to give me one little theorem, right? The way you prove it is you say, look, I'm going to prove something for every data point. So I'm going to fix x and r vector. Then the only randomization left is the random draw of the action. Right? So we're going to randomly draw the action for each individual event. We want to know what this estimator is for the randomly drawn action. So the expectation is equal to the sum over the actions of the probability of the action. The probabilities cancel now. And the sum is going to cancel with the indicator function. And you just end up with the reward of the policy's chosen action. Okay, so this is a proof that it's unbiased. And that's a proof that, in some sense, that you can avoid doing an A/B test to discover how good a policy is. So that's fantastic, right? All right, so this is an actual example of using data. I think this line here is an offline estimate of the system's actual performance, and this black line is the actual performance of the system online. There's some differences because of statistical variation, but nevertheless it's quite convergent. And this is the policy that we were competing with, which was editors trying to choose news articles. Up is good. Okay, so are there questions about this? This is a really powerful trick in my experience, and so I want to emphasize that in many situations, if you collect the right data, you can avoid doing an A/B test to discover whether or not you have a good policy. And furthermore, we'll be able to learn from that, and we'll be able to do much more. Right? So for much of this, you'll have to go and look at the tutorial I showed you earlier. But the ability to avoid an A/B test is amazing in terms of how productive you can be in solving a problem. Questions? Yeah?
So I believe with multi-arm Bandit, one limitation with them is they have the stationary assumption, so basically that the conversion rate sort of has to be static, which for most websites is not true, right? The conversion rate at 2 a.m. on a Wednesday is different than Saturday at 5. Is that a problem that's faced here as well?
So this is one of those things where, okay, so there's the theory. There's actually two branches of theory. One of them is when the world is IID, and the other one is when the world is adversarial. So the adversarial theory applies regardless. And there's also the practice. And in practice, what happens is when the world is non-stationary, you increase your amount of exploration a little bit, and it copes with that. So even though the world is non-stationary, and so the IID theory doesn't apply, you can still end up doing pretty good performance-wise. I think Claudio has a question.
So, John, sometimes what happens in practice is that you don't know these probabilities, right? Because what generates the data is some policy that somebody else has. Asking about how to sort of cope with this problem. Would you actually estimate that probability by the policy? What would you do?
Yeah, so there are a lot of techniques for trying to estimate the probability. In practice, I find it really hard to trust whatever results you get out of them because they're all subject to the quality of a prediction, which you can't even verify very well. What I would primarily suggest is, say we go here, we go here. We have a new client library here, which is designed to generate these probabilities. So get them to use this, and then you get the probabilities, right? So this might seem like a flip answer, but I've been frustrated many times trying to work with existing data. If you just have the wrong data, then it's so much worse than actually having the right data. This is a client library which is designed to collect the right data, and that makes it much, much easier to start being productive. Another question?
Back to that example, here's what exactly we predicted, because multi-arm bandit need a finite number of outcome options, right?
Yeah.
So I'm guessing we're not predicting every news article.
Yeah, so we've applied it in situations where there's relatively small, so the editors are not actually useless. They actually have a real value. The real value is choosing what the top 20 articles are. And then the system is trying to optimize which one you're most interested in.
So then you start from scratch every time a new 20 article is chosen?
No, it doesn't start from scratch. So we use action-dependent features. So if you featureize your articles in the right way, then it'll carry over from past articles.
That's nice.
Yeah. Okay, let me show you one last thing, and then we'll give it a wrap. Let's go here. Okay, so this is contextual bandit data. So this was generated by using the same supervised data set. So we're using the same ground truth as before. And what's happening is there's a action that was taken. There's the costs of that action. So we're operating in a loss basis rather than a reward basis. And there's the probability with which that action was taken. So I think that initially we just randomly happened to choose action 1 several times. But then later we choose action 2. And sometimes we see a loss of 1, sometimes we see a loss of 0. So this is the label information here is different. The label information here is what you get out of, for the purpose of training a contextual bandit policy, right? Now we can say, oh, we have a contextual bandit with 2 actions, and I'm going to use the same flags as before to train, right? So the system is operating by reduction to the same base learning algorithm. So, and we're using the same kinds of flags. So you expect similar performance, except for whatever issues there are associated with erasing information when doing contextual bandit. Because you have less information. You only have the loss of the action that was actually taken, not implicitly the loss of all actions. Right, so there's less information available, and yet still you can see that our performance is not that bad. We're down to 5% error rate, and it will get better. You can see the system is working harder because there's a bit more work involved in reducing this down to a supervised learning solution. But nevertheless, we get pretty good performance. So what I'm trying to show you here is that it's extremely practical to solve contextual bandit problems along the lines of what you're used to with supervised learning. And that means that you can go out and you're free to solve new kinds of problems that you maybe didn't even know that you could solve previously. Anyway, thank you. Yeah, sure.
We have time for a few questions. Yeah, we have time for about maybe 5 questions. So, who's up? We have time now for 4 questions.
So, a company I used to work at used Vocal Wabbit very extensively. So first off, thank you. I like it. Secondly, I never got a straight answer on the name. I think it had related to the poem Jabberwocky.
Yeah. Yeah. Okay, so the name. Jabberwocky is one part. Elmer Fudd is another important one. And the last part, let's see if I can do this. Let's go here. Let's search for killer rabbit. Yes. Aha, yes. This, oh, I don't know, maybe we're not getting sound because, oh no, here we go. Ah, yes. So in Jabberwocky, there's a Vorpal sword, which is where the word Vorpal comes from. It's a nonsense word. This is kind of the point of the poem. But nevertheless, you know it's a very sharp sword from context.
Right. Keep me covered. What with? Just keep me covered. Too late. There he is. Where? Here. From behind the rabbit. You silly son. What? You got us all worked up. Where's the ordinary rabbit? That's the most foul, cruel, and bad look you ever seen. I know. You, Kate. I saw my armor, I was so scared. Look, that rabbit's got a vicious streak a mile wide. A killer. Yeah, he'll do you a treat. Oh, yeah? Manly. Stop, Kate, I'm warning you. What's he do? Nibble your bum? He's got really sharp. He can leap about. Look at the bone. Go on, boy, chop his head off. Right, silly little beater. What's rabbit to do? Coming right up. I warned you, but did you listen to me? Oh, no, you don't. Well, it's always the same. I always tell you. Right.
All right, so that's the third reference in the name.
Anybody in the back? Because I know you're all the way down there. I haven't seen your hand. Anyone have a question in the back? In the middle? In the front? Yes. 2 right next to each other. How convenient. I saw stars here first.
So is there a continuous outcome instead of a classification equivalent? Is there like an easy way to adapt it to linear instead of a classification?
So what I think you're asking is, can you do contextual bandits where instead of having discrete actions, you have a continuous action?
Yes.
Yeah. So the answer is yes, and the answer is no, it's not in VW. And the answer is we actually have a paper that we're submitting to Colt in 3 days, which is trying to crack a big part of, trying to make these things much more practical. So that's an active research area. So this finished, it's 4.7%. It was 4.5% doing supervised learning. Give you a sense of how close it is. Yeah?
How does this compare to adding some randomization to your training data and then doing classic offline training?
How does it compare to adding randomization into your training data?
Like, so for example,
So the purpose of adding randomization into your training data is usually for regularization purposes. Right? So you're adding it in to make sure you make it less likely to overfit.
we can also do it to do against selection bias. You can show some random results that you're not normally showing. And you keep track of, use IPS the same way, but feed it back into your offline training data.
I see. So you can add randomization into your training data, and you can learn a policy, and then you can deploy it, and then it will go and it will do something, and then you'll feed the data back into your learning algorithm. I mean, we're trying to do the same thing, but we're trying to do it in a more scientific way, right? So we try to add just the randomization which is required, only the randomization which is required in order to give you the performance that you want to get, right? So I guess I would regard that as flying by the seat of your pants. Well, here we actually have theory behind the algorithms, and we know that we'll be able to converge in an effective fashion. And another thing which is happening here is that if you add randomization to your training data, you get out a model, then you won't know what the implicit distribution over actions created is. So here we create an explicit distribution over actions. That means we can draw from it and we can know exactly what that P should be. And so having that explicit P is very powerful. It's related to what Claudio said. If you don't know what that P is, you can try to estimate it, and it might work, but it's tough.
One more?
This is kind of small, but one thing that's kind of been burning is that watching you go through these is you'll do like a test of every next example, given the model's current state, but at the end does it like back test through the rest of the data set just to get, it's fully trained set at that point?
Yeah, it's not doing that.
Okay.
Obviously, you can save the model and do it if you want, but it's not doing that.
I guess I'll ask a question. I know we have a lot of R and Python users here, probably Julia and other languages. Are there any bindings to other higher level languages, or is it all command line?
I mean, there's Python, Java, C#. Those are the primary bindings that exist.
Okay. With that, I will say thank you very much to our speaker.